reaction rate and rate law. In this video we will define the rate of reaction and the rate law. The rate of reaction is intensive property, it does not change with the size of the system, and our reaction term, which will appear in the general mole balance. This one is an extensive property. And the rate law, which you already know, this one relates the reaction rate and the concentration of the reactants. Let's have a quick overview. The rate of reaction tells us the number of moles of a component generated or consumed per unit time per unit volume. N refers to the number of moles and the subscript refers to the component. Suppose we have the reaction A goes to B. Let's write two expressions for the reaction rate. One with respect to the reactant and the other one with respect to the product. For the reactants, the reaction rate expresses number of moles consumed per unit time per unit volume. Similarly, for the products, the rate of reaction tells us the number of moles being produced per unit time per unit volume. Note that for the reactants, this term will be negative since the number of moles of reactants is decreasing. For the products, it will be positive. So we can see that the expression for the reactants is somehow more interesting. By convention, we want the disappearance term to be positive, so we add a minus sign to both terms on both sides. Minus on the right to make the term positive and minus on the left before R to indicate a disappearance. The reaction rate is an intensive property. It does not change with the size of the system. It is also independent of the reactor type and independent of a process. Let's do an example to show how the reaction rates for reactants and products relate to each other. We have a reaction 3A plus 2B go to 5C. If at a particular point the rate of disappearance of A is 15 mole per liter second, what are the rates of B and C? So the reaction rate can be expressed as the rate of disappearance of the reactant or as the rate of formation of a product. Let's first express the rate of reaction for the reactant A. Since we are dealing with the disappearance of the reactant, we have a minus sign in front of R. The actual value is then positive. If we wanted to express the disappearance of A in terms of rate of formation, so as if A was a product, then signs have to change. Then the rate of formation of species A is RA, positive, which indicates formation, and the actual value, which will then be negative. How the reaction rates of products and reactants relate to each other is expressed with relative rates. Here we need to take into account the stoichiometry of the reaction. Stoichiometric coefficients stand in the denominator and are negative for the reactants and positive for the products. The reaction rate tells us the rate of production or disappearance of a component per unit volume. We are very much interested to know what is the actual production or disappearance rate in our reactor as a whole, not only per unit volume. For this purpose, we introduce a term R, big R, which is a term we will use in the general mole balance. It is an extensive property since it changes with the size of the system. The more reacting mixture we have, the more product is produced or consumed. And the units are moles per second. This sounds like a unit for a molar rate. Now we need to be careful. The first equation assumes that reaction rate is uniform throughout the reactor. So this reaction works fine. Since the reaction rate may vary with the position, we need to account for this change. We must integrate over the entire volume in order to obtain the actual production or consumption rate. And don't forget to add a minus sign if the component is being consumed for the disappearance, that means. From the kinetics, you already know that the relation between the rate of reaction and the concentration of the reactants is expressed by its rate law. For nearly all forward irreversible reactions, the reaction rate is proportional to the product of the concentrations of the reactants, each raised to some power. The power the concentration is raised to represents the order of the reaction with respect to that component. If the reaction follows an elementary rate law, then the stoichiometric coefficients are the same as the individual reaction order of the components. So in this case, the reaction would follow an elementary rate law if alpha and beta would both be 1. The rate law is independent of the reactor type and is determined experimentally by following the concentration of the component at a particular time during the reaction. Rates of most reactions are very sensitive to the temperature. This is due to the temperature-dependent rate constant. Most reactions increase rapidly with increasing